This is the first type of example that we did in class the other day, an inelastic collision with two vehicles heading towards an intersection at 90 degrees. So a 4,000 kilogram car traveling east, we'll label this M1, with a velocity of 25 meters per second, V1, collides at an intersection with a truck that's traveling at 5 meters per second, V2 north. And we'll label this M2. So we'll list out our variables. And the first thing that we have to do is calculate the total momentum of the system before. Now, since this is in two dimensions, we have to calculate the total x momentum and the total y momentum before the collision, because due to the conservation of momentum, the x momentum has to be conserved before and after, and the y momentum has to be conserved before and after. So, I'm going to calculate the total x momentum. That comes out to 100,000 kilogram meters per second. If you notice, there is a velocity for the car, but there's zero velocity for the truck because the truck is going north. It's not going in the horizontal direction at all, so it has no x velocity. So now I need to do the same thing, but for the total momentum in the y direction. And you'll notice now the car has zero velocity because the car is traveling in the horizontal direction, not in the vertical direction. And the truck has a velocity of 5 meters per second because it's traveling in the vertical direction. So we have a total x momentum of 100,000 kilogram meters per second and a total y momentum of 50,000 kilogram meters per second. So I can tell right now that if these two stick, they'll be traveling at an angle that's less than 45 degrees because there's more x momentum than there is y momentum. So the next thing I need to do is look at this as a before and after picture. If these two combine, they're going to produce a before x momentum and a before y momentum, and when they combine, they're going to travel some way in this direction. And that direction has an x component that is the same as the px that I just had, and a y component that's the same as the py that I just had before and after. So if I translate that y component over to here, I get a triangle, and I have an angle, and I can find this momentum here, which I'll label PF. And once I find that momentum, I can combine the masses to find the velocity of this vehicle. So the first thing I want to do is use the Pythagorean theorem to find that final momentum after by using the two components. And I get a total final momentum of 111,803.4 kilogram meters per second. I didn't put the x and the y momentums in here because I'm running out of space, but the x that I used here was the 100,000 and the y that I used here was the 50,000. And when I Pythagorate them using the a squared plus b squared equals c squared formula, I get 111,803.4 kilogram meters per second. Now that I know that, I can use that momentum plus their combined masses to find the velocity. And I get a velocity of 8 meters per second. Now, I combine the masses right here. It was 10,000 plus 4,000 for the two vehicles together because it is an inelastic collision, which means they do stick. Now that I have the velocity, I need to find the angle, which is just a matter of going back and using these sides. Now, I technically have all three sides of the triangle. However, this one's been rounded a couple times. The px and the py have not been rounded, which makes tangent, which is adjacent and opposite, the best choice for finding this angle because it does not have a rounding error involved in it. Any choice, sine, cosine, or tangent, would create a correct answer, but the tangent is the most correct answer. So this is what the angle would look like. So we have an angle of 26.6 degrees made from the horizontal that these two objects would travel stuck together at 8 meters per second. Okay, this example is like the one I did in class, but I didn't take pictures of the one on my board. I thought I did, but I'm going to replicate this one. It's very similar, and I'll go through it step by step for you. So a 2 kilogram ball traveling with a velocity of 2 meters per second collides with a 3 kilogram ball that's at rest. So this is what it looks like. After the collision, the second ball moves with a velocity of 1 meter per second at an angle of 30 degrees below the horizontal line. So this is the direction that the second ball will travel in, and I labeled it V2 prime. Remember, the prime establishes it's the same, it's a V2 variable just like before. The V2 variable here was 0, but now it's a prime variable, which means it's like a before and after. This one's traveling at 30 degrees. So at what velocity and angle will the first ball travel? So as shown here, I want to know what this v1 prime is, and I want to know what this angle is between the two. Now I've drawn the after situation in red. So what I need to do is first establish my before momentums. Okay, I need the x momentum before and the y momentum before, because according to the law of conservation of momentum, the x and y momentums will be conserved after. So first things first, let's get a variable list for the before situation. Now that I have a variable list, I can solve for my x momentum before and my y momentum before. So I do a momentum for the system, m1v1 plus m2v2, and for the first object it does have a velocity, so 2 kilograms times 2 meters per second. The second one, however, is a stationary object, so its momentum is 0 because its velocity is 0. So the total momentum in the x direction is the momentum of the first object, m1, and that's 4 kilogram meters per second. Now there's no calculations needed for py because neither object is traveling in the y direction, so there's no y momentum at all, no net y momentum for the two objects beforehand, so that's 0 kilograms meters per second. Now that I have these, I need to look at the afterwards situations. First thing I have to do is break up these two momentums, the m1 momentum and the m2 momentum afterwards, into components that I can look at. So what I did was I took the p2 momentum, the momentum of this second object as it travels downward, and I broke it up into a p2x prime and a p2y prime components. I then did the same thing for the first object that's traveling in this direction. Its momentum I broke up into a p1x prime and a p1y prime, and that's at an angle of theta, which we'll need to calculate. Now that we know that there are components for these two momentums, we actually need to work on some relationships between the y components and the x components, and that relates back to these two momentums over here. So let's take a look at what those relationships are. So for the components, we know that the total x momentum beforehand is 4 kilogram meters per second, which means the total x after has to be that as well, which means the x components of both of these have to add together afterwards to equal 4 kilogram meters per second. We also know that there was no y momentum before, which means the net y momentum after has to be 0, which means these two components, the y components, have to add together to equal 0 kilogram meters per second, which also means that they'll have to be equal and opposite. So if I can find one, I know the other. And if I can find one x component, I can subtract it from 4 to find the other. So that's exactly what we're going to do. First, we're going to find the momentum of this second object, since we know its mass and its velocity afterwards. Then we're going to break it up into its components. So first, let's find its momentum after the collision for m2. And its momentum, since it's a 3 kilogram object times 1 meter per second, is 3 kilogram meters per second. So that's the momentum of this second object. Now with the 30-degree angle, we can break it apart into its two components. So the x component, which is p2 x prime equals p2 prime cosine 30, comes out to be 2.6 kilogram meters per second. The y component comes out to be 1.5 kilogram meters per second. Now, you might want to take a snapshot of this picture because I'm going to go to a new slide. What I need to do is relate these to those other components in the first object. If you remember, from these relationships up here, if p2y prime is 1.5, p1y prime has to be 1.5 also, but in the other direction, which would make it negative technically, so this is 0. If p2x prime is 2.6, then p1x prime has to be equal to whatever the difference between 4 and 2.6 is. So we'll calculate those, and then we're going to have to work backwards. If we find these two components, we can use the Pythagorean theorem to find this momentum, and then we can use that momentum to find the velocity, and we can use these components to find the angle as well. So we'll do that on the next slide. So what I've done here is I've redrawn the information we had over on the other slide. I redrew the pictures with the components, the two components that we found for the second object, and the relationships. So now we need to find the components for the first object. We're going to start with using this relationship of the x's to find p1x. So by subtracting the 2.6 for the p2x prime from the 4 total, I get p1x prime to be 1.4 kilogram meters per second. I'm now going to use the relationship for the p1y prime and p2y prime, which equals 0 total, for the p1y prime. Since they're both equal and opposite, I could put a negative in here, but I don't need to because when I do the Pythagorean theorem, it's going to square out the negative. So it's 1.5 down for the second object, 1.5 up for the first object. Now that I know these two, I can plug them in to the triangle that I have above and use the Pythagorean theorem to find p1 prime. So, since the p1y prime is 2 kilogram meters per second now, I can use that along with its mass to find the velocity of that object. And I nicely get a 1 meter per second for v1 prime for that for the first object that's on the top. Now I'm going to use the two components to find the angle. Again, like the last example, I'm using those two for tangent because they deal with one less calculation. They went from here to here in order to get the hypotenuse, so it's just one less round of rounding, no pun intended, in order to find the answer. So it's all three, sine, cosine, tangent will give me the correct answer, but tangent will give me the most correct answer because it has the least amount of rounding. So I end up with an angle of 47 degrees, which is above 45 degrees, which I know is to be at least that part correct because my y component was bigger than my x component. So these two examples will hopefully help you solve the workbook problems that I put on the website that you'll do instead of a lab report for this week.